Hi, this is Paul again. I'm going to call this video 3D Printed Platonic Order phi HEXPENT 1. In my last few videos, I showed that the DNA nucleosomes were based around the duo phi vector system. In front I'm showing an icosahedron, and it's got 612 vectors, and they're all different colors because these colors can be used for keeping a sequence. Now I'm going to show you the dodecahedron, and that has got 1020 vectors, and they're the same. The colors are arranged for a sequence. But these vectors use two colors because out of 5 colors, the 20 vectors are permutated in colors. Vectors for the dodeca and the vectors for the icosa should be kept in synchronization because they are basically a dual vector system, and the colors should be kept okay. It is easy to make a mistake of getting the colors out of whack. I've used a size 3 icosa, and I've made the colors giving hexagons and pentagons of different colors. First I'm showing the triangle, showing the hexagon, and the triangle is made of 2 different colors. On the far side, not shown, the triangle is 180 degrees different, so the colors are switched around. Now the 12 vertices of the icosa show a colored pentagon. So now we have a duo phi HEXPENT system. So let's give this beautiful icosa with lots of colors a spin around. Now there's something I'd like to also add. If you look at these triangles, they come in a pair, and each pair is 180 degrees difference. So the 2 colors are flipped around also. Now I've been studying this arrangement of hexagon and pentagons, and I've decided to use a 3D printer and turn out a hub. So I'm showing in front the 2 halves of a spherical hub. Now look how the top and bottom halves are made so that they fit perfectly together. I've provided on this sphere 20 hexagon sockets, tapered sockets, which are the vertices of the dodecahedron. I've also given it 12 pentagon tapered sockets. These can be used for the vectors of the icosahedron. Okay, now I'll show you what I got from the 3D printer. I'll show you the bottom half of the sphere to start, or you can call it hemisphere if you want to be posh. Okay, as this is spinning around, you can see I'm showing the 10 bottom vectors of the dodeca. You can see that it's spinning around on the yellow and red vertical axis. Now if you study the geometry of a dodecahedron, you'll see that the top axis is a Y-shaped and the bottom axis is another Y-shaped. Now these are 180 degrees about. The yellow and red vector rod has got a tapered hexagon on the top and a tapered hexagon on the bottom. My printer is a Dremel printer, but it only prints one color. That's why I've put 2 sleeves of different colors on the rod. Okay, so now we'll bring in the top half. So then we've got 20 vectors for this dodeca, the full sphere. Now if you take a look at all these vectors sticking out from the sphere, you can see that the pentagon sockets are evenly distributed around the sphere. So when we put them vectors, it's going to balance everything around that sphere. There are some theories on YouTube 369 that shows 9 vectors around a circle, but that is not 3-dimension like this. This is a 3-dimension system that does the same. And many scholars say, oh, the order is in the hidden dimensions or higher dimensions. It looks like they've looked down their nose at this 3D Platonic order for almost 10 years. Maybe because I don't have a school tie. Okay, so now I'm going to bring in the vectors for the icosa. So now we give it a spin around and you can see that the vectors seem to be well balanced all around the sphere. Now what you're looking at is the first prototype of this arrangement. I realized that the length of the vectors and the thickness can be improved to make it more presentable. But this is basically like a world atlas. It's an indication to give you the color codes in perfect organization around the sphere, just like the countries on the world atlas. It has to be kept universal for other people to get the right color combinations correct. I showed in a video a few years ago the DNA metro around a sphere, and I showed there was a wonderful mathematical sequence. But the mathematicians of the forum said only a crank would work with trivial geometry that nobody understands. Who do these people think they are? Because I don't see any light shining from them. Anyways, let's get back to the toy. I showed in my earlier videos a DNA spider, I called it. This was a vector spider. Let's take a look. In front of you, I show a vector hub. And you can see that I provided 12 pentagon tapered sockets. These tapered sockets work out perfectly. They are just like the sleeves that are found in the machine shop. Now this hub can be broken down into single bends, but we'll get to that later in the video. So now I'll add the colored vectors and give it a spin around for you to look at it. So you can see this is basically a simple toy, but these vectors are golden ratio to each other. They're phi vectors, and I've showed in my videos over the years that these vectors are very important for stuff like DNA infrastructure. So now I'm going to show you how this stuff came out of the 3D printer. So as you see, the 3D printer has turned out some pretty good results. I think the 3D printers are gonna bring people into 3D geometry like nobody has ever seen before. Because none of this interest in geometry has ever come out of the chaos theory. And for the guys that are interested in 3D printing, I am using a Dremel 3D40 printer. And I also use Simplified 3D for doing the support stuff. I think we are only scratching the surface on this uncharted territory. I've got a lot of stuff I'd like to show you again, but that'll be in another video. So this is Paul saying thank you very much for looking at my video.